All right, welcome back to the DP curriculum. This is my lesson 14, structure 1.4.2. Today we're going to be covering masses of atoms, how they're compared to the carbon-12 isotope, and we're going to talk about relative atomic mass and relative formula mass. By the end of this, our goal is to be able to determine the relative formula masses from relative atomic masses. And a couple of things to keep in mind is there are no units to relative atomic and relative formula mass. Furthermore, the values that we use are on the periodic table in your data booklet, and you should always be using up to 2 decimal places as is shown in your data booklet. With that said, let's jump into the lesson. So when we talk about relative atomic mass and relative formula mass, one of the things we do is we think about how we measure things in real life. So usually we measure items by mass. If you're baking something, you may weigh out 350 grams of flour or something. Generally, we use kilograms or maybe grams, but the SI unit we tend to use is kilograms. But the thing is, chemical entities, which is a word we used last lesson, but in lesson 13, but chemical entities are small. And when I say they're small, I mean they have very, very little mass. Very little mass. So instead, we use a different system of measuring. So we use a relative relative system of measurement, which is actually a lot closer to what we normally measure. When we're using kilograms, there is actually a weighted item that we use as the international mass of 1 kilogram, and all weights that we use are based off that. All our scales are based off that. So what we say when we say it's relative is it means we're comparing mass to something else. So our relative system is based off carbon 12. So you may remember from when we discussed isotopes in like lesson 7 or 8 or whatever, that carbon 12 specifically means that we have a carbon atom, and this 12 denotes the mass number, which means there are 6 protons and 6 neutrons. There's also 6 electrons. However, this has negligible mass, full mass. So basically, all the mass comes from here, which weighs 12. And we say that every single mass we use in chemistry comes from this. So, for example, hydrogen is not really, doesn't really have a mass of 1 if it's just 1 proton, but we say that hydrogen 1 is just 1/12 of our carbon 12. So all our mass comes from carbon 12. So that's what this first standard means. Masses of atoms are compared on a scale relative to carbon 12. So carbon 12 is our standard, and we say carbon 12 weighs 12. Everything else comes from that. That's how we get our protons, each weighing 1, and our neutrons, each weighing 1. Not, it's not the other way around. It's not that protons weigh 1 and neutrons weigh 1, so carbon 12 weighs 12. It's actually that because carbon 12 weighs 12, the protons and neutrons each equal 1. It's a little bit backwards and it seems a little confusing, but all you really have to know for the DP is that everything comes from the carbon 12 atom. How do we actually use it? Well, we use that to calculate, we use this to calculate relative atomic masses, and we use relative atomic masses to calculate average mass of isotopes, average masses of an element, and that's what we call our A sub R on the periodic table. On the periodic table. So when you look at your periodic table of some element, let's say, for example, we have oxygen, 8 protons, and it says 16.00. That 16.00 is our relative atomic mass. This is all stuff we've done before. So the new adaptation here is relative formula mass. Whoops, that looks a little combined. Relative formula mass, which we use capital M sub R. Relative formula mass deals with more than one atom. So the relative formula mass of an object is just equal to the sum of atomic masses that make up said object. So for example, A sub R of oxygen, we mentioned earlier, right up here, is 16. However, in our atmosphere, the air we breathe is actually O2. And so for O2, we would, instead of finding the atomic mass, we would find the relative formula mass because the chemical formula for oxygen is 2 oxygen atoms. So we would take 16.00 plus 16.00, and we would find that M sub R equals 32.00. So that's it. Relative formula mass is quite simply the sum of the masses of the thing that makes it up. You may also sometimes hear this as molecular mass or ionic mass, but the DP has just decided that we put these two terms together to talk about uh, formula mass. So with that done, all that's left to do is some examples. So we'll jump right into some practice problems. So the first practice problem is let's look at table salt, NaCl. So the question is, what is the relative formula mass? If you want to try it yourself, pause the video right now, give it a shot. Otherwise, I'm jumping in right now. Well, sodium has an atomic mass of 22.99 as found on the periodic table, and chlorine has an atomic mass of 35.45. Again, also found on the periodic table. It's helpful to have one with you when you're doing this. To find the molecular mass, I'm just going to add these two values, and I will get a grand total of 58.44. And there we go. Once again, you may notice that, of course, there are no units to these values. Atomic mass and formula mass do not have units. All right. So with that done, let's move on to problem two. Problem two is going to be a bit more difficult. For problem two, we're going to look at a complex formula. So this is quite simple. It's one positive ion, one negative ion, a cation, and an anion, just two atoms. We're going to look at Ca3PO4 2. This is known as calcium phosphate. So calcium phosphate, what we have to do is try and figure out the molecular mass of this one. So there's a couple things we need to figure out. First is, what is the atomic mass of each part? Well, that part is easy because we look at our periodic table and find that calcium has an atomic mass of 40.08. We find that phosphorus has an atomic mass of 30.97. We're using up to 2 decimals. And oxygen, we already know, is 16.00. The issue is there are multiple of these. So much like we did with oxygen, when the 2 was down here, that meant there were 2 oxygens. So we had 1, 2. So we're going to use that same logic to find out that we have 3 calcium. So we'll multiply our 40.08 times 3. Our phosphorus, on the other hand, it looks like there's 1. And there is 1 in the term phosphate. However, we have this 2 outside of parentheses. So this 2 actually modifies both subscripts, the subscript for the phosphate and the subscript for the oxygen. And it modifies it like multiplication. So we're going to have 2 phosphate and we're going to have 8 oxygen. So now using these values, we can find the mass of each section. So that is exactly what I'm going to do. 40.08 times 3 is 120.24. 30.97 times 2 is 61.94. And 16 times 8 is 128.00, again, maintaining two decimal places. And then I just add these numbers up, and I get a total of 310.18. And this is my relative molecular mass of calcium phosphate. All right. Well, it's a short video today, but hopefully this helps, and have a great day.